This project is a finger or hands-free tap turner. It is an assistive biomedical device designed to help people with limited hand strength turn faucet handles more easily. My name is Kayashta Das. I am a master's student in materials engineering with a background in mechanical engineering and experience in CAD, FEA, 3D printing, failure analysis, and computational chemistry. I was especially motivated to work on this project because I have family members who have arthritis and have suffered a stroke. Many people with arthritis or stroke struggle with grip strength and limited hand dexterity. That makes turning faucet handles painful and sometimes impossible. So, since that is part of an essential daily activity, I wanted to design a solution that improves independence and ease of use. So, in particular, the device is built to target crystal head faucet handles, crosshead faucet handles, and single lever faucet handles. These types of taps are also frequently found in older households or lower income households. So this project can greatly benefit lower income individuals as well. My proposed solution is a hands-free tap turning device that can fit multiple faucet handle types. The idea behind this is to let the user turn the faucet using their wrist or forearm instead of relying solely on finger grip or finger strength. So how does the device actually work? The device clamps onto the faucet handle and is equipped with a bolt and nut mechanism that can be used to further tighten it in place. Once attached, it stays fixed on the handle and
This is
gives
a
the
video
user a
of a
larger,
wrist
easier
or
surface
forearm
to apply
assisted
force
tap
along the
turner
lever arm.
where you don't have to
And this
use
video
your
will show more
fingers
details about how it
to turn
works.
a tap. And this is particularly useful for people with arthritis and stroke. So this attaches to the faucet handle and grips it tightly. And there are ridges on the inner side of this for better grip. And instead of using your fingers to turn the tap, you put this down onto tap, and the grooves on the side are meant for better gripping of certain tap types of tap handles, like for example crosshead taps or lever taps. And it grips onto the tap tightly, and you can use your forearm or wrist to push this to open and close the tap, as shown in the video in the PowerPoint. Following this, there's also a bolt threaded into a dowel nut, which was inserted into the device itself. And there's a hole in that dowel nut which the bolt is threaded into. Furthermore, you can tighten the bolt to make it easier to grip a particular size of tap handle, or you can slacken the bolt if necessary. This makes it easier to turn a tap without pain, particularly if you have arthritis in the fingers or limited mobility due to stroke.
And these two videos will demonstrate how it works in practice, opening and closing a tap. Summarize some key features of the device include the ergonomic lever, internal ridges for grip, an adjustable clamp, and a compact housing. It is also 3D printable, low cost, and designed to stay more hygienic through the vented opening at the top of the device. Now, to really evaluate performance of the device, I performed finite element analysis to estimate how this design would behave in real life. So from literature, the operating torque that is typically required to open or close a faucet is equal to 2.1 Newton meters. Therefore, in this study, I used 4 Newton meters to represent a maximum loading condition. Therefore, if the PLA prototype could withstand 4 Newton meters, it can definitely withstand the typical loading of 2.1 Newton meters in reality. And the inner cylindrical contact surface was fixed to simulate attachment to a faucet. This setup approximates real-world loading during operation of a faucet. The findings from this were that the maximum stress was well below the PLA yield strength. This indicates that the device is structurally safe under expected loading conditions in reality. Additionally, a displacement analysis showed that the maximum displacement was approximately 4.5 millimeters at the tip of the lever arm under the highest applied torque of 4 Newton meters. So this level of deflection is noticeable but acceptable for a PLA prototype, especially as stress remained well below yield strength. And this indicates that the device is structurally safe under expected loading. Overall, the prototype successfully does what it was intended to do, and that is to allow a tap to be turned using one's wrist or forearm. That reduces strain on the fingers. In the future, the product can, however, be further modified to be made of metal. A rubber lining can be added on the inside of the housing for improved grip and scratch prevention, and the device can be tested more broadly amongst different users and different faucet types. In conclusion, this design offers a simple, low-cost, and practical solution for people with reduced hand strength. Compared to other products on the market, this one has novel advantages in that it bypasses finger gripping and can be turned using the forearm or wrist. And furthermore, it is ventilated for hygienic bathroom use. It has proven to be, through simulation analysis using FEA, very effective for patients with reduced hand strength, as the FEA analysis showed that it will hold up in real life well below the yield strength of PLA. And these are all sources used, including for images within this presentation. Thank you.